In this video, what I want to do is motivate the electromagnetic radiation in astrophysics course. Why do we run it, and why should you be wanting to take it? Well, from an astrophysical perspective, there are three main reasons. The first is that light is what we detect and what we use to infer what is going on in the universe. Obviously, we can't go to these faraway astrophysical systems, so what we have to do is collect light, manipulate it, and figure out what's going on. So how can I look at this image of the Eagle Nebula and tell you that I know the blue stuff here in the middle is about 10,000 Kelvin? How do I know that the material out here is more like 10 Kelvin? Can we somehow weigh these pillars of material and ask whether or not they'd be able to produce stars, for example? How is this region evolving over time? How do we know things, quantitative things like this, from light alone? Answering that is a key aspect of this course. This is just another example showing the M31 galaxy in the UV, the optical and the mid-infrared, and you can see that it looks visually different in these different wavelengths. We're going to understand why, and we're also going to understand how these different wavelengths can help you build a more complete picture of what is going on in astrophysical systems. Things also evolve on very long timescales in astrophysics. What I've got here is an animation of a cloud that is going to collapse under gravity to make a young star. And around that star, there will be a rotating planet-forming disk. You can see it starting to be produced here. Now, the actual amount of time elapsed in this movie is going to be on the order of millions of years. Okay, so if we were to observe this process happening in reality, we would only see a single frame of this movie, just one single snapshot. How then can we make a movie like this and say that the disk is spinning? How do we know that that's the case? So we have to use light somehow to infer the kinematics of things in astrophysics, how they're moving. And we're going to also study in this course how we do that. So number one, and one of the main reasons for wanting to do this course, is that light is what we use to interpret things in astrophysics. And that applies to every single area of astrophysics. Number two, though, is that light can affect the dynamical evolution of astrophysical systems. So just going to give you a few illustrations of that in action now. The first one here is an exoplanet that is transiting its parent star. That means that if you're looking at the star, the planet is periodically passing between you and the star, making it look a little bit dimmer. Now, normally, when we find planets transiting, the star maybe gets 1% dimmer. In this case, the star is getting about 20% dimmer. And the transit also has a very funny shape. Well, it turns out that that is because this planet is so close to its parent star that the light from the star is causing the atmosphere to be blown off of the planet. So you get this tail left behind of material, which means, and it also is great and puffed up. So as the planet transits, you've got this big cloud coming off of the planet, which covers a large fraction of the star's surface and makes it look a lot dimmer. And also the tail follows behind, so that's why the transit shape ends up being funny. So here, the light from the star is affecting how the planet evolves. Light can also affect how star formation happens. So here again is going to be two movies with exactly the same initial conditions, so they're identical at this stage. And what they're going to do is collapse to make some stars. And on the left, we're going to ignore what the light from the stars does. And on the right, we're going to account for the fact that big stars emit a lot of UV light. And that can strip electrons off of hydrogen atoms, ionizing them. And that process heats the gas up to about 10,000 degrees. So what you have is a very hot bubble here, which is at higher pressure than the surroundings, and so it expands. So you've got a very hot, high pressure bubble. You've got pillars and things being formed with the young star cluster in the middle here. Whereas the simulation, which was exactly the same to start with, where we ignored the effect of the light, looks very, very different. So just stick in your head what these two things look like. And then let's go and look at a real young star cluster, the Eagle Nebula again, and ask yourself which one looks more like reality. We have a young star cluster here, we have a big bubble, and we have things like pillars as well. So we don't just use light to infer the temperature here and how things are, and how massive, for example, these pillars are. We actually have to understand how light affects matter to understand how it got like this in the first place. The young stars here have blown this great big hot bubble that's expanded. Now, the young stars are the ones trying to produce planets, and they are found in those kind of hostile environments like the Eagle Nebula. And that same radiation that can blow away the star-forming gas, heat it up and blow it away, can also shine upon the planet-forming disks and strip them of material too. So this is a gallery of what we call proplyds. The disks here are being shone upon by strong radiation fields and having huge plumes of material driven off of them. And this reduces the amount of time you have to make planets, it reduces how much mass you have to make planets, and could have a big impact on explaining the different types of planet populations that we're finding around other stars. Now, this is my main focus of research, so we'll definitely be returning to this in subsequent weeks. So far, we've talked about planets and about star formation. At the other end of the scale, more cosmological scales, the effect of light on matter is also really important for considering the reionization of the universe. So you have the Big Bang, the universe is very ionized, and then it recombines and becomes very neutral. But then you start to produce stars, galaxies, supermassive black holes, and they emit a lot of this high energy UV radiation, which can ionize the gas again. So what you're seeing here is a simulation of a big box of universe that started off neutral, and then as the stars and the galaxies and the black holes form, their feedback, their radiation that they emit, is starting to ionize the universe again, which is the blue stuff, is the ionized parts of the universe. So understanding the dynamical effect of light on things from planets all the way through to the entire universe essentially is something we're going to be looking at in this course as well. Finally, in terms of astrophysics, light also affects the chemistry of astrophysical systems. So what I have here is a star shining upon a cloud, and this panel over here is showing what the chemistry of this cloud would be like at different depths into it. So the squiggly lines here denote how strong the UV radiation is. So here it's very strong, and then as we go deeper into the cloud, the UV gets weaker and weaker and weaker, and then there's none over here. So on this near side of the cloud to the star, where the UV is very strong, you get that ionization going on. So the hydrogen atoms are losing their electrons, and the gas ends up being about 10,000 Kelvin. But as you progress deeper into the cloud, you get shielded more and more from the UV radiation. So your ions start to recombine with your electrons to make atoms. And eventually, as you go deep enough into the cloud, you start making molecules, and eventually your chemistry can start getting very complicated. So the amount of radiation affects the chemical makeup of astrophysical systems too. And this is also something we'll look at. So in summary, number one, light is what we observe in astrophysics to infer quantitative things, and we're going to be looking at how we do that. Number two, light affects how things dynamically evolve in astrophysics, and we're going to look at that as well. And number three, light affects the chemical makeup of gas, and that is another topic that we'll look at as well. And this is going to be important, the stuff we're going to do for any topic in astrophysics, from cosmology right the way through to planets. Just leaving the astrophysics behind for a second, the stuff you're going to learn in this course is also useful outside of astrophysics and academia. So I did my PhD at the University of Exeter, and the astrophysical code that I used there and still use today has now been turned to skin and breast cancer research. So the idea of modelling how light propagates through matter in space can be applied to how light propagates through skin. It's just different scales and densities, basically. Another astrophysical code turned to useful, well, I would argue all these applications are useful, but turned to sort of real-world applications is a group in St Andrews have applied an astrophysics code to tackling COVID. So they asked the question, can we find a wavelength of light that would destroy a COVID virus but not hurt human skin? With the idea that you can maybe irradiate rooms, leaving people safe but destroying the virus. And again, this is an astrophysics code turned to a non-astrophysics application. Radiative transfer is also becoming important in the video game industry with things like ray tracing. We're going to be doing things like writing ray tracing codes. They obviously will not be to the same level of complexity as the video game industry, but the fundamentals are going to be the same. How light affects the atmosphere of the Earth is very important for climate modelling. So here are just some snapshots from the UK Met Office website. So they have a big code that tries to predict how our climate is evolving. And again, the fundamentals that we'll look at here would apply to this kind of model as well, in understanding how the light from the sun influences our atmosphere and our climate evolution. And finally, There's also things like canopy radiative transfer. So this is light shining upon forest canopies, and it's important for understanding things like what it does for remote sensors, so satellites, what they would see, and also for understanding how forest canopies can evolve as well and survive in different environments. And there are a whole host of other applications. This is just a handful. I was talking to a builder the other day, and he was saying they have things like light sensitive setting sealants and things like this. So the applications are really numerous for what you're learning here beyond astrophysics. So to summarize, the course material here is really important for any field in astrophysics if that's what you're interested in, but is also going to be much more widely applicable too as you go on to do other things perhaps. So hopefully you're now well motivated, and I look forward to seeing you full of energy and enthusiasm in lecture 1.